So in this problem solving session, I'm going to focus on the sample mean and decide to do and resolve some problems that you might encounter in this subject. So what I'll do is I'll take collection of random variables y1, let's say y1, y2 up to yn, and they're all IID, exponential, let's say with parameter 1, random variables. So that means, what does it mean? That means the distribution of y, y1, y2, yn, any of the yi's, probability yi less than or equal to y, is given by integrating out the exponential density. So that's from 0 to y of e to the minus x dx for y non-negative, and at 0 otherwise, right? That's the definition of the exponential density. So I'll just move this to the middle, and let's say the question I ask you is, the first question I ask you is, what is E of y bar? That is, E of y bar means where y bar is the sample mean, where y bar is summation I equal to 1 to n yi divided by n. So I sample y1 to yn, and I want to compute what E of y bar is. So let's look at the answer a little bit. It's quite easy to do. So E of y bar means what? E of y bar is the same as E of the sum from I equal to 1 to n of yi divided by n. Okay? And that's going to be equal to what? 1 over n, because the expression is linear, summation I equal to 1 to n, expectation of yi. Right? Now, each of the yi's has the same distribution, exponential. So that means they're all the same quantity. So this is going to give equal to 1 over n times, I can take any of the yi, so I'll take E of y1. So the n cancels off. So what do I get? I get E of y1. What is E of y1 going to be? E of y1 is just 0 to infinity x times e to the minus x dx. And what's that going to be? You integrate by parts. So you do integration by parts. And what you get? You get this first one will be x minus e to the minus x from 0 to infinity, and minus 0 to infinity, and you differentiate the x, that's 1, and then the minus e to the minus x dx, right? And that, if you do it, it's just at 0 it's going to be 0, at infinity also it's going to be 0, because this will take over. So this part is just 0, and then minus will become a plus because of the minus sign there, this minus sign here. So you'll get 0 to infinity e to the minus x dx, and that's just minus e to the minus x from 0 to infinity. I plug in infinity, I get minus infinity, and I get minus of minus e to the minus 0. So I'll just get 0 plus 1, and the answer is 1. So the mean of y bar is just 1, same as the mean of y. So the mean just scales. Sample means expectation under the original distribution is the same as the original distribution itself. Very good. Now, if I ask you a question, what is the variance of y bar? Okay. How do I do that? So I do it the same way. The variance of y bar is variance of same notation is summation I equal to 1 to n of yi by n. That's what y bar is, right? So that's the variance of y bar to find out. But here what I do, and I know in variance it scales quadratically, right? So the first thing will be 1 over n squared times the variance of the sum from I equal to 1 to n of yi's. Now here is where I'll use the fact that the yi's are independent. If they're independent, then I know that the variance of the yi's is just sum of the variances. So it's 1 over n squared times summation I equal to 1 to n of the variance of the yi's. Right? Because that's just a definition of that just follows from the properties of independent random variables. But each of the variance of yi is same as the y1 because they're all the same distribution, right? So this is the same as now as all the yi's are all distributed exponential 1. So what I can do is I can replace this guy as 1 over n squared times n times the variance of y1. So that's going to be equal to what? 1 over n times the variance of y1. So how do I find the variance of y1? So now variance of y1, let's try and do the calculation. Variance of y1 by definition is what is expected value of y1 minus the mean of y1, the whole squared, and its expectation. But that's the same as expression of y1 minus 1 the whole square. That's what we found out here, right? This is the mean of y1 was just 1. The same calculation like you did here. This part right here. So let's go back. So here it's e of y1 minus 1 whole squared. So it's going to be equal to 0 to infinity x minus 1 the whole squared e to the minus x dx. Right? So let's try and do this calculation. Is just going to be equal to integral 0 to infinity x squared minus 2x plus 1 times e to the minus x dx. So now here's a calculus exercise to do this integral. Maybe I will allow you to think about how to do this yourself. So if you want me to do this calculation properly and then do the integrals, you would have to do the 3 integrals. You'll have to do it like integral 0 to infinity x squared e to the minus x dx minus 2 times 0 to infinity x e to the minus x dx plus 0 to infinity e to the minus x dx. And if you do the whole integral, you will get that this is also going to be equal to 1. So I will leave this as an exercise to do this. This is a calculus exercise that you can do. So now the variance of y1 is also 1. So that means the variance of y bar, we start off with this person, was equal to 1 over n the variance of y1. So it will be 1 over n times 1. So therefore, the variance of y bar, the answer to the question is, it is 1 over n. So now you notice there's a very interesting development here, that there's a reduction in the variance. That is, as n gets larger and larger, the variance gets smaller and smaller. Whereas the mean stays always to be 1. So if you look at the mean of y bar is always going to be 1. There's no change in the mean of y bar, but the variance always reduces. It reduces by 1 over n. It's an interesting fact to keep in mind that this happens with the variance. Now let's do a simple thing. So now let's ask, let's see, suppose I want to understand what's the chance that y bar is at least, let's say, some distance from 3. Let's say some 3 by 1. What's the chance of this guy? Now maybe I'll do a little simpler one. I just do y bar minus 1 is bigger than 1. How far is y bar from its actual true mean, which is y bar is 1? What is that going to be? So now if you do this calculation, you can use Chebyshev's inequality. Right. In this, what would you do? You would again do probability of y bar minus 1 bigger than 1. 1 is the mean of y bar, right? 1 is the mean of y bar is equal to 1. So by Chebyshev's inequality, this is less than equal to the variance of y bar divided by 1 square. And that's exactly what Chebyshev's inequality will tell you. And that's going to be equal to what? That's going to be equal to 1 over n. So it's quite a very powerful inequality, that the probability that y bar minus 1 is bigger than 1 is less than equal to 1 over n. That means the chance of finding y bar away from 1 is going to go to 0. So therefore, the limit as n tends to infinity, the probability of y bar minus 1 bigger than 1 is going to go to 0 as n goes to infinity. This is going to have a nice fact about the sample mean. It concentrates around the true mean, which is what you have seen in the law of large numbers as well. So we can see that explicitly as well here. So let's take an epsilon positive. So let epsilon be given. Then we know that the chance that y bar minus 1 is at least epsilon, this quantity is going to be less than equal to, by the same argument at the above, it's just the variance of y bar divided by epsilon squared. And the variance of y bar is just 1 over n times epsilon squared. So therefore, limit as n tends to infinity of the chance that y bar minus 1 is bigger than epsilon, this goes to 0. Because 1 over n times epsilon squared goes to 0, and goes to infinity, goes to 0. Right? So that's the same as saying that that y bar converges to 1 in probability. This is another fancy way of saying this. This is true for every epsilon positive. It's an interesting fact we have seen. So what all have we seen in this problem session? We have seen that, sorry, let me go back here. Let me get this line out. So what we start off with exponential random variables. Then we computed its the sample means actual true mean. So we found out that E of y bar was actually equal to 1. Then we tried to find the variance of y bar, and then we found the variance of y bar was 1 over n. That means there's a reduction of 1 over n for every n. So as n gets larger and larger, the variance of y bar is going to go to 0. From this, we found out that the mean concentrates around the true mean. So therefore, that is, like we check here, we can check other side. So the probability of y bar bigger than minus 1 bigger than 1 was less than or equal to 1 over n. That goes 0. But we found out that if we take any epsilon positive also, probability y bar minus 1 bigger than epsilon is less than or equal to 1 over n times epsilon squared, and that goes to 0. So this is a sort of an application of Chebyshev's inequality in that sense. So let me now do a little bit more general idea. It's called order statistics. Let me write it down. Called order statistics. So here the principle is the following. Suppose I have a sample y1 to yn. So y1, y2, yn is my sample. Let's again take IID exponential 1. Now, what I could do is I could say that I will go and order them, right? I will order them from the lowest to the highest. So I do a sample and some numbers come. They're all random numbers, so they will come at some number. So then I'll have to go and find the order. So let's say order them. So, but I say same names. Let's say we order them and we use the same name. We use the same, like y1, y2 is second smallest, and yn is the largest. So in some sense, you can think of y1 as the minimum of y1, y2 up to yn. Y bracket n is the maximum of y1, y2, yn. Very good. That's all. Now suppose I go and ask you, like, can you find the distribution function of yn? Right. So how do I do that? So suppose I ask you, the question I ask you is, can you find the distribution function of yn? And let's just give it a name. Let's just say y and all IID. Let's say IID random variable is y, and y is exponential 1. So how does one do this problem? Let's just do it slowly. So now I want to find out the chance that y of n is less than or equal to y. What is that? That's the same as the maximum of y1, y2, yn is less than or equal to y. Right? Now, the moment I have this, then this is going to be equal to, see, if the maximum is less than or equal to a number, then everybody has to be less than or equal to a number, because not even one of these yi's can be above this guy. Right? So that's a simple exercise. So simple exercise to just check this out, that this is the same as probability that all the yi's I equal to 1 to n, yi is less than or equal to y. Only then it can happen that the maximum is less than or equal to y. But this means what? This means that, but now you can use independence, right? So I can use independence of yi's, they all IID, right? Independence of yi, to say that this guy is going to be equal to the product of I equal to 1 to n, the probability of yi less than equal to y, right? Because independent, these events are independent because the y is independent, so you can write the product of the probabilities. But now each of them is the same, so it's going to be probability of y less than equal to y, the whole power n. So one fancy way of saying it is that if f sub yn of y is the distribution function of yn, so that is, this happens, that's the same as you look at the distribution function of y and raise it to the power n. So it's one nice way of understanding the distribution function of yn. So the maximum is just like an nth power of the single random variable y. So that's a kind of a nice answer to this distribution function. Now similarly, once you know this, you can ask various questions. Like for example, I can ask a question, let's say the same way like before, I can ask what's the chance that yn, let's say, is the largest number that I get from the sample is, let's say, 5. Let's say it's 5. And then it beats 5 by at least 1, let's say. Well, I want to ask what is this number? So the way one would do this is the following. So one would have to take it as, so look at this probability of yn. Look at the event first. Let's forget the probability. The event yn minus 5 bigger than 1 is the same as yn minus 5 is at least 1, or minus of yn minus 5 is at least 1. Right? That just means that that's equal to saying that yn is at least 6. That's from here. Or here, yn is less than, so if we do the calculation correctly, so this becomes plus 5, goes that side, it's minus 4. Right? Only then that will happen, that only yn less than minus 4 will this happen, that you will get that. So yn less than 4 or minus 4, let me just do it properly, sorry, just slowly. So it's like minus yn plus 5 is at least 1, and that's equal to saying that yn is at least 6, or yn is less than minus 4. Very good. Right, no, yn is less than minus 4. Yeah, less than minus 4. Very good. Less than plus 4. Sorry. Very good. This is what you'll have, right? So there are two possibilities. If yn is less than 4, it's at least by distance 1 from 5. If y at least 6, so that means if you want to calculate the probability that how much is yn away from 5 by at least 1, that you don't have to do Chebyshev's or what, you can do directly or Markov, you can do directly the probabilities. That's the same as the chance that yn is less than 4 or yn is bigger than 6. This is all, I have to make a small mistake here. This is all this order statistic, not the actual yn. I'm sorry about that. So I do this, and that's the same as probability that yn is less than 4 plus probability that yn is at least 6, and that is the same as what now, you know the density of yn, so the distribution function of yn, that's going to be equal, is just same as fy power n. So you write this as probability of yn less than 4 plus 1 minus the probability of yn less than equal to 6. Since we are in the continuous variable setting, it's the same as f of y of 4 to the power n plus 1 minus f of y of 6 to the power n. That's what you get, right? That's the answer from this calculation. Let's call this calculation as 1. That's how you get it. This is using 1. Of course, now you can go and find out what fy4 is. So what is fy sub y? F sub y at a point y is just the probability that the exponential is less than or equal to y, and that's the same as 0 to y e to the minus x dx, and that's just 1 minus, so let me do the integration properly. So it's equal to e to the minus x and a minus sign from 0 to y, so it's 1 minus e to the minus y. So therefore, what we find, the probability that the order statistic, maximum order statistic, is 5 or away from 5 by 1 is going to be equal to, from this expression right here, is going to be equal to fy to the power 4, that is 1 minus e to the minus 4 to the power n plus 1 minus plus 1, and then inside is going to be again minus 1 minus e to the minus 6 to the power n. And that's your answer. There you go. Very nice. So there's some simple exercises one can try. One can try this, for example. If you try to understand the distribution function of let's say yr, let's say, right? So if you want to understand, so I'll give a sketch for this. Suppose I want to understand, let's say 1 is less than equal to r is strictly less than n, and I want to understand the chance that yr is less than equal to y. That is the odd order set is less than equal to y, right? So that's the same as, if you just think a little bit, it's this exercise. That's the same as the probability that at least r of the yi's are less than equal to x. Only less than equal to y. Only then you will have that the random variable y sub r, the rth position order statistic, is less than equal to y. Now there's a simple exercise to do this. I will not. I will just allow you to check my book to see how to finish this off. This is the same as. So you can just check the same as. All you do is you need at least r, right? So you just take. I can have 1 or at least up to r, right? So sorry, at least r is mean r to n. You'll have r up to n random variables are less than equal to n. So you choose j of them. So that's n choose j. And you have j of them less than equal to r, so that's the same as f sub y of y to the power r, and then you have 1 minus f sub y of y to the power n minus r. So that's the density, that's the distribution function of the order statistics of y sub r. This is something you can check. It's not that hard to do. If you're having difficulty, this is done in 8.1.1 of my book. So section 8.1 of the book has the example done. But it's a nice exercise to try. The rth order statistic also gives the same answer. Okay, thank you.